Okay, hello everybody. This video is going to be about a Yamaha YA-27 tonearm. This was the predecessor to the YA-32, exclusively used in the PX-2. This particular tonearm came out of a Yamaha PX-2 turntable, a straight line tracker. And what I'm going to be discussing is the frictional characteristics of the drive mechanism, as well as some of the belt characteristics. And well, let's get started. I'm going to show you the voltage required to keep the motor above stall speed under varying conditions. The first condition is going to be without a primary drive belt, and this is the primary drive belt. Okay. That's not to be confused with what I call the final drive belts, which are these big wide belts here. Okay, so I'm going to show you the voltage required to keep the motor just above stall speed. What you're going to need to do is you need to zero in on this drive pulley here. This black set screw will be the giveaway that it's rotating. Okay, so watch out for that black set screw and you'll see what I mean. Okay, here we go. I'm going to be increasing the voltage. And you can see the motor turning, and that's 58 millivolts right there. So 58 millivolts is the approximate required to keep the motor just above stall speed. And you can see how smooth that is. It looks like the motor did stall on me, so I need to go a little bit higher. Right around, that should be about stall speed right there, 75 anyway. Okay. Alright, so we're at 61 millivolts and the motor's rotating smoothly and being kept just above stall speed. But that's with no primary drive belt, so all the drive mechanism is disconnected right now. That's just the motor free turning. So it does stall right around that one point where we can't see the set screw go around the backside. So I know this motor here, after it's been serviced, will stall right around 75 millivolts. So let me get it right around there. Okay, 74 millivolts, and now we have consistent rotation, 360 degrees around consistently. Okay, you can see that, right? Hopefully. Alright, next thing we're going to do, we're going to bring the voltage down. And by the way, we're driving this with a Tektronix PS280 regulated DC power supply, so our DC voltage is nice and pure and clean, so this is a valid test. Okay, so motor's still rotating at 74 millivolts. Okay, I'm going to drop the voltage to 0 and put the primary drive belt back on so we can see what this thing does when it's driving all the rest of the drive mechanism. Okay, check the belt to make sure that it's not twisted. Everything looks good. And I'm going to redo the same test. Here we go. Okay. We should be seeing about 300 to 310 millivolts in order to avoid stall. So you have to forgive me, the vernier control on this Tektronix DC regulated power supply is not exactly the most easy thing to work with at these low voltages. But generally speaking, we're looking at around 300 millivolts for a stall speed on this freshly serviced. And I want to emphasize that because your motor stall speed is going to be much higher in voltage prior to servicing these things. So actually it's doing better than previous tests. Previous tests were indicating about 310 millivolts minimum required with the full drive mechanism connected. But this, it's now doing even better at about 270 millivolts. Okay, so I think it's safe to say that we can establish a 270 volt, not volt, millivolt minimum required to keep the motor from stalling with the full drive system connected. And this is relevant because it's an indicator of the amount of friction and other issues present, undesirable issues present in the tonearm drive mechanism that would, if they were less than ideal, it would require a significantly higher amount of drive voltage in order to keep the motor from stalling. So what we're seeing here is nice smooth operation with a very low required minimum drive voltage, currently at about 268 millivolts. And the carriage is moving, although very slow. I will try to demonstrate that to you with the scale rule. The scale rule is graduated in 32nd inch increments on the top scale and 64th inch increments on the bottom scale. I'm going to try and put it close to the carriage here so you can get an idea at the rate at which it's moving. Currently it's moving at approximately the rate that a record groove would bring the carriage across left to right, or right to left more exactly. And so, you know, we're doing really well with this. If this carriage were not moving the way it is now and sticking and carrying on with you know, with a drive system that just wasn't working very well, what would happen is that it would generate a fairly significant tracking error, and then all of a sudden the motor drive voltage would have to overcome its stall. The voltage applied to the motor would have to be higher in order to overcome its stall, and then it would suddenly jerk across. So in other words, it would kind of crab walk. So you get this kind of business, and then it would drive the voltage up to probably 2 volts or something, and then it would pop across, stop, and then repeat the process over and over again. But this is the kind of characteristics that we want. We want a drive system that is extremely smooth, minimum friction, and no binding and jerking like this as it moves across. Okay, we want it nice and smooth, and that's what we're getting right now. And it's not only due to all the servicing that I've done in the drive rollers and gear reduction mechanism and the motor and so forth, and replacement of primary drive belt and all that. But it's also due to these custom belts that I've made. These belts are extremely flexible and do not consume very much torque in the drive system at all. And so I'm very happy with it. I'm not necessarily going to settle on these for future upgrade modifications, but it's something very similar to that. I'm going to discuss belts a little bit later. Right now I just want to show you the rate at which this carriage is moving. I won't be able to do that unless I zoom in. So let me reposition this carriage into a better place for the camera. And I apologize if my words in this video are less than coherent. I don't do scripted videos. It's just the way I insist on doing things. Raw and unedited. Shame on me, I guess. But alright, so here we go. Let's try to make this happen. And what you should really try to do is pay attention to this corner here. and its relation to the gradations on this scale rule. Again, these gradations are in 32nd inch increments. Here we go. Let me zoom in. And who knows if this is going to focus. Won't focus. Can't do anything if I can't get it zoomed in here. I don't know if lighting would make a difference. It just won't focus. Well, that's about as zoomed in as I'm going to get. Let's go ahead and continue this test at the risk of being left bad feedback on YouTube. Again, I apologize, but you know, I'm not a camera expert, so and my camera probably has limitations there regarding proper focusing with video. Okay. So we have a drive voltage going to it of 258 approximately millivolts. Oops, stalled. That's a little low anyway. Normally it takes about 300 millivolts to avoid stall with a fully connected drive system after it's been serviced anyway, and with these special belts that I'm using. Everything interacts together. Okay, right now we're at 292 millivolts, and we're about to run over the scale rule. Don't want to do that. Okay, and it's the same if we reverse direction. Okay, in this direction I can actually go a little bit lower than the current 295 millivolts, which is the direction, of course, that it's that you know that it moves for playing a record, of course. So this is even better. And we're avoiding stall at 257 millivolts applied to the motor. And you can see that the rate that the carriage is moving is a little bit faster than what the spiral inward movement of an average LP record is going to produce, but not much. This carriage is moving pretty slow and pretty darn smooth. I wish I could zoom in better, but I can tell you with all honesty that the carriage is moving very smoothly with no stop and start jerky crab walking kind of movements. It's very well behaved. So I guess you'll just have to take my word for it. Okay. Hopefully that proves to you that my Yamaha straight line tracking tone arm rebuilds do produce an improvement. Okay, if that doesn't prove to you, then I'm not sure what else will. Possibly a future video where I just go into further detail with what I do and stuff. Okay, it did stall, but you know, that's to be expected. I mean, we're running way down near stall speed, and it's trying to engage the inner limit switch, so that increases friction just a little bit. So all it takes is the tiniest little bit to stall the motor. So anyway, but you have a really good idea now what's required to drive the motor to keep it from stalling. Okay, we're going to move on to something a little bit more interesting now. and zoom out. And we're going to talk about these belts, and hopefully that'll come out okay, because you're going to need to listen to the sound of what's going on here. I'm going to have to shut down this DC power supply to get the sound level as low as possible in the room. Okay, here's what we got. As you can see, we have 4 belts hanging from a test jig, and this belt here is the original belt. You know that because it's got the holes in it where the rivets, the load spreader plate and rivets were. Okay, so you see that. This belt here is a about a 62 thousandths thick belt of the same construction as the original belt. But the original belt is thinner, though, at approximately 50 thousandths. This is another material here. And I don't want to discuss these materials in detail, okay? You're just going to have to forgive me on that, but I'm not ready at this point to discuss these because I do not have a modification service in line yet for this, and I need to think about it more and possibly change things a little bit more. But basically, this is another belt material, sorry, I get tongue twisted sometimes. This belt thickness is approximately the same as the original here, but a different formulation. And then this is the belt that I'm using here. You can see how flexible this is. It's very limp, it's very limber, okay? And this is what we want, because as it has to go around these drive rollers that are approximately 3/8 of an inch thick, in diameter, it consumes power, it consumes torque going around there. And so we don't want to do that, because every time it requires more drive force, then we're looking at slippage from the drive roller, which is this guy right here. And we certainly don't want that. These things have a very strong tendency to produce, to exhibit slippage issues, as you well know, I'm sure. And so this is what I'm using, and again, I'm not going to discuss exactly what it is at this point, but it works really well. It requires a minimum amount of tension, which is what we're looking for. Tension is going to produce a guitar string type effect, and we don't want that. So we certainly want to minimize tension, yet maximize the amount of interface friction between the drive roller and the belt so it doesn't slip. There's another thing I want to show you too. I can put this on a incline, approximately 30-degree incline, and prove to you that this drive system works the way it should, with no slippage when used normally. Now, one of the most important things, remember, this is about approximately 62 thousandths inch thick. This is approximately 50 thousandths inch thick. And this is approximately 50 thousandths inch thick too, and this is, I don't know, probably about 40 thousandths, I think. So anyway, here's the interesting thing. We can apply a mechanical stimulus, and we can hear the intrinsic sound of that belt, which partially shows its damping and other characteristics of the belt. The Young's modulus and so forth, and mechanical impedance, but anyway, mass, so forth. But we can get an idea of the characteristics of this belt when hit with a stimulus, and since sound waves are a stimulus too, it is somewhat relevant to, it's kind of a basic primitive test, but anyway, it gives you an idea. So I'll shut up. Okay, are we all clear on what these 3 belts are doing? Now, check this out. What do you think of that? It's almost like it's not even there, like it's comprised mostly of just air. So that's a very good thing, because when we do another test and we put our hand up here, or we could put an accelerometer or whatever, but if we're basically looking for the amount of energy being transmitted through the belt up into this fixture here, we can feel it. We can feel it coming through. Okay? On all three of these, basically. Not this one so much, because this one's pretty light, and it's lighter than these two belts. It's a different formulation. We hardly feel anything much coming through there, but we definitely feel it here, and the most with this thicker 62 thousandths belt. Okay? But then when we do this, nothing. I can't feel a thing coming through this wood fixture, this test fixture, as you would expect. I mean, look how flexible it is, look how light it is, okay? Look how much inherent damping it has. These guys just want to make a statement on their own, right? This guy, transparent, doesn't do anything. I mean, relatively so, anyway. Okay, so I think I've proven to you that the belts are an important part in keeping vibration out of the carriage, because if I'm putting an impulse of energy into one end of the belt here and it's transmitting along its length up into the fixture, well, guess what? Anything that's coming through the base plate, it's going to want to make it up into the carriage even more so. Now, granted, of course, we have these rollers that are in direct mechanical hard connection to the base plate, but the more that we isolate this, the better. Okay? Other modifications in the future could attempt to look into that. But also, too, I mean, what residual motor vibrations come through the transmission, the gear reduction mechanism, it's going to want to find its way into the carriage via the belts. Okay? So the better it is in this regard, the higher performance sonically that we can expect. Again, the other benefit is that it takes much less energy to move this belt across the rollers than it does these thicker, harder belts, okay? Including the original YA-27 belt, which is the same belt as used in the YA-32 as well. The length dimension might be a little bit different on the YA-32, but the formulation is the same, thickness is the same, everything. Okay, I think that pretty much covers the belt story. Let's put this thing on an incline and see what it does. And by the way, I always do this incline test on every Yamaha straight line tracking tone arm assembly that comes through here that I service. Okay, whether it be YA-32 or YA-27, it must pass this test. And this is approximately 30 degrees. And obviously you're not going to be using your turntable under those conditions. Nevertheless, I always demand that my tone arms pass this test. Okay, let's see what we got here. Okay, so we'll bring it down, and just for reference, right now we're at 5 volts. Okay, so that's the speed that you can expect a carriage to move at 5 volts applied. Okay, there we go, and we're going to apply 5 volts again. 5 volts. Okay. Climbing right uphill, 30-degree incline, no problem. Okay. Reverse direction. Bring her back down. And I don't know why you'll need to see this, but I'll reduce the voltage. You never know what people are going to want to see. So right now that's approximately 1 volt applied, going uphill no problem. Alright. Other things on this particular tone arm, you know, limit switches, you know, I go through all those and make sure that's all functioning properly. One thing I should tell you too, when you get one of these tone arm assemblies back from me, I'm expecting you to be familiar with the service manual calibration procedures to some extent anyway, but the procedure you need to be familiar with is the adjustment of this VR4 pot, and that will set the running tangential alignment here. So if when you put this all back together and the tone arm is biased inward or outward as it's running, then you're going to need to look at the VR4 pot. Now I supply instructions and everything for that, so I really shouldn't need to cover this in this video, but anyway, I just figured I'd tell you. That's the VR4 pot there on this circuit board, this green circuit board that the ribbon cable is plugged into. Of course, I also rebuild these photo transistors here and the slot type photo interrupters. So let's see here. Let me show you that a little bit while I'm at it. I can't show you the whole thing because it's obscured somewhat by by the shutter. So anyway, but there's 3 photo interrupters here, 1, 2, and then a third one you can't see under here. And these go bad regularly on YA-27s. YA-32s not very much, but YA-27 tone arm assemblies, yes. Again, YA-27s were used only in the PX-2s. So I have changed many of these guys out, and I provide a service for that. Okay, I think we're done. I've bored you enough. I don't think I need to discuss anything else. I think that's about it. Alright, well, thank you for your time. I appreciate it very much, and have a great day. Thank you.